Welcome back for the our last bit prior to the performance. Adjust you. Oh yeah.
We have the technology. We still have the technology.
All right. So it is my pleasure to introduce Bob Slevc from the University of Maryland in College Park. Bob did his undergrad at the University of Colorado with a double psychology and Chinese major, and then went to do his PhD at the UCSD in psychology with Vic Ferrer. I also worked there a bit with Ani Patel, who came up in our talk a little earlier. He's done lots of language music research. He then spent, was it a year at Rice?
3 years.
3 years at Rice in Randy Martin's lab as a postdoc. And is currently running a lab doing very cool stuff, the Language and Music Cognition Lab in the Psychology Department at the University of Maryland, where he's an assistant professor. So today we'll hear common structural processes in language and music. Please join me in welcoming Bob Slevc.
Thanks for having me here. This has been really interesting so far. It's pretty exciting to find a bunch of people with interest in this language. So there's an old quote that's been attributed to a lot of people, including Elvis Costello, which is that writing about music is like dancing about architecture. And you could probably say the same thing about talking about music. I often find this like a little bit depressing, but I got to think about it, and I thought, well, maybe dancing about architecture isn't so boring. Like it could actually, it turns out there's even an Australian TV show called Dancing About Architecture. I don't know what it's about. Maybe it's about music. So let's dance. So I'm talking about structure in language and music. And why would I want to talk about structure? I mean, this has already kind of been set up, but what's kind of interesting about both language and music is that you can characterize them both as rule-based systems, right? So they seem to be, you can sort of talk about them as this way of using defined structures to combine kind of basic elements into this sort of infinite number of higher order structures. And this is interesting by itself, but it's also interesting because they both seem to be universal to humans and, at least to some extent, specific to humans, especially structural processing. Now, this is not undebated, right? So you can find cases where people have tried to teach some aspects of syntactic structure to starlings with some degree of success. You can debate how much. There's maybe some evidence that, for example, the rock hyrax has a kind of syntax in its mating calls. You can also talk about rhythmic structure, right? And you can find some animals that can synchronize to rhythm who maybe seem to have some understanding of rhythmic structure. But I think that even the people who are the biggest proponents of these kinds of findings will agree that they are not showing structural creativity anywhere near the degree that humans use it. And so that means that we're left out with animal model, right? And as a psychologist, I love animal models. Animal model, because I'm a reductionist, right? If you could make something extra simple and put it in a cage and measure it with like some kind of food pellet reward, then we can really learn something, right? So it doesn't seem like we can do that with language and music, but maybe you can learn something by the comparison, since they have a lot of things in common. So what do I mean about structure in language and music? So, I mean, we've sort of talked about this already, but you can think about linguistic syntax as combining discrete elements into hierarchically organized sequences, and you can do that in language with things like words. You can do that in music with things like notes or chords. You can use what are potentially very similar, maybe exactly the same kinds of formalisms, which I will not go into, but we'll hear about soon. And so this raises a pretty straightforward question for a psychologist, right? Which is, well, the same kind of cognitive or neural processes involved in processing these distinct kinds of structure. Well, maybe, right? So there's been some evidence that might be suggestive that there is. So if we go neural, there's now kind of a growing collection of findings that suggest that musical structure seems to be processed in areas that are sort of canonically thought of as language areas of the brain. So this is a harmonic priming study by Barbara Tillman that shows activation in something that looks a lot like Broca's area and its right hemisphere homologue. On the other hand, there's these well-documented dissociations between deficits of language processing and music processing. Now, these deficits are not usually, haven't been really investigated at the level of granularity that lets you say whether it's a syntactic deficit in language and music or structural processing, but nevertheless, there's clearly some separation. And this will look familiar. So one way that you can reconcile this, Adi Patel proposed this, geez, now 10 years ago, I guess, is with the shared syntactic integration resource hypothesis, which is a really nice hypothesis with a really terrible acronym. SURH. So according to SURH, you have these distinct representations, right? Like nouns and verbs, parts of speech. Right? There's no real obvious musical analog to parts of speech, and there's no real obvious linguistic analog to, say, chord functions. But you might imagine that you integrate them into these sort of time-spanning hierarchical relationships using the same mechanisms. And so that's these shared resources that might be involved. So now there's been a growing collection of studies that have tried to test these SURH. And the basic prediction is one you got just out of the last talk, which is that if you present musical and linguistic syntactic difficulty, whatever that means, you make things hard in both sort of language and musical syntax at the same time, you should get interactive effects, right? If you have some limited kind of resource that does this sort of processing, then when you tax it from 2 domains at once, you're going to get interference. Now, because you have me up here, I'm going to tell you about a version of this that I did, instead of everybody else did. And what we did was look at garden path sentences. So, and we did this while people heard chords that were either harmonically expected or unexpected. For many people here, this will be boring, but garden path sentences are a kind of sentence that has a temporary syntactic ambiguity, right? So something like this. So because language, you process language in this sort of incremental way, then if you read or hear the scientist, you probably think, okay, that's a good subject. Confirmed is a nice verb, the hypothesis is an excellent object, and now you have this verb was, which, it's sort of unclear what to do with, right? And what you have to do is realize that this verb is actually, the hypothesis is not the direct object here, it's the subject of an embedded clause. Right, so this is a embedded sentence complement. So this is, your classic sort of garden path case where you have this temporary syntactic ambiguity. You can, at the point of the hypothesis, you have 2 potential kinds of structures that could be going on. Now you can contrast this with a full relative clause just by using the complementizer that. And so now in this case you could say the scientist confirmed that the hypothesis was false, but you can't say the scientist confirmed that the hypothesis yesterday, right? So the hypothesis is unambiguous in that case. So this gives you a nice way to measure the amount of sort of syntactic complexity that is induced by this grammatical ambiguity, this temporary ambiguity, by just looking at how fast people process the disambiguating word, in this case was. And we're going to do this with reading time. Now there's some argument about exactly what the garden path effect reflects. You can talk about it as revision and reanalysis, which is kind of a classic story, that you went with the preferred interpretation of the hypothesis as a direct object, and now you have to throw that whole thing out and go and rebuild a new structure, and that's a lot of syntactic work. You can talk about it being sort of probabilistically driven. You can talk about it as being, 2 structures that are active simultaneously, that are competing, which takes a certain amount of resource to resolve. But in any case, whatever you're doing that's hard is something that is hard syntactically, hard because of the structure. So what we're going to do is have people read sentences that either are or are not syntactically ambiguous at the same time they hear chords. So this is very much like what you just heard from Nicole and John. And let me just show you what it's like. So here's kind of a schematic, but when we're just going to manipulate the key, whether the key matches or mismatches during that critical region. And it's self-paced, so people just hit a key or a button for each next segment. So it works something kind of like this. Hopefully this is not painfully loud. Okay? So that's the idea. You have people read a bunch of these sentences. You have the garden path sentences, you have the controls, you have the fillers. And the predictions, right, for the shared processing, just to revisit this again, is that you should predict some kind of interaction. So if, in fact, processing sort of key structure information, stuff about musical key, relies on the same kinds of resources as processing garden path sentences, then you would imagine that this garden path is going to be especially difficult to deal with when you have also this sort of surprising key chord. Okay? And so what I'm going to show you are difference scores. So what this is showing is this is the difference between the garden path and the control, the that sentence. So this is how much slower you are to read was when there's a garden path, or when there isn't a that versus when there is a that. So this is your standard garden path effect here. Not a huge movie, but this isn't that terrible of a sentence. And this blue is when it's paired with all in-key chords. But here's what happens when you have a pair with this out-of-key chord. Right? Your garden path effect is considerably larger, so you have this significant interaction. So this suggests that whatever it is that you're using to, whatever kind of mechanisms are involved in resolving garden path sentences are taxed in some way by this surprising chord. Hooray! Sure. But you might say like, well, oh yeah, sure, okay, so that's, that out of key chord is sort of linguistically, like it's unexpected in terms of or musical structure, but it's also just kind of weird, right? Like maybe it was just surprising and it kind of distracted you and you're pushing these buttons and you have this like, kind of moment. Yeah, I mean, it's kind of unclear why that would only affect the garden path sentences, but nevertheless, it's a potential concern. But there's a nice way to control this, which is just to use some other kind of manipulation that isn't structural in the music, right? So it's something like this. Right, so the idea is that should be probably as surprising, but it's not surprising in a way that's structural in any real obvious way. And in fact, you don't get any interaction. So the garden path effect doesn't differ as a function of whether the disambiguating region occurs with a piano or an organ. All right, so we're doing good. Everything's great. You might want another control, right? Maybe you're like, garden path sentences, like maybe they're a little bit weird. Maybe this would happen with anything, right? Maybe something about a key violation that just interacts with language manipulations, whatever they are. So you can test this with the violation of semantic expectancy. So it's the same idea, same exact paradigm, except now instead of using garden path sentences, we're just going to use things that are semantically unexpected in that same region. So the boss warning, we watch for angry pigs. Right? There's nothing structurally wrong with that. It's a perfectly reasonable syntax. It just happens to be sort of semantically not what one might have expected to find there. So here you get a semantic unexpectancy effect, just like you might expect. People are slower to read pigs than dogs. But that doesn't interact with the key of the accompanying chord. And that's also true if you use an organ chord. Okay, so I sort of went through this quick. This is these are old data, but the important finding here, right, is that you get this interaction only when you have a sort of structural manipulation of language and a structural manipulation of music. You don't have to do it when you have a non-structural musical manipulation like timbre, or when you have non-structural linguistic manipulations like semantic expectancy. So this is all looking pretty good for the SSI range. And that's how I felt about it for a couple of years. And then, I mean, there's a couple things going on here, right? So one thing that you might notice is there's the main difference between these sentences, of course, is that one of them is a structural ambiguity and one of them is this sort of semantic manipulation. But the first one, this requires more than just sort of structural surprise or something. This really seems to require some kind of revision, right? Like you commit to some kind of structure and then at some point you have to kind of be like, oh, that was wrong. This doesn't, right? I mean, when you get pigs, that's weird. But you don't have to adjust anything about what you've done up until that point, right? And what you might think a better control would be what you might call a semantic garden path, where you rely on semantic ambiguity. So you could say, the old man went to the bank to withdraw his net, right? And the idea is that until you get to net, you probably think financial institution minus control like riverbank. Then when you get net, you have to sort of be like, ooh, not that kind of thing, right? And it turns out, in some work that just came out recently, it turns out that if you use this kind of manipulation, you get exactly the same kind of interactive effect that we found with the syntactic garden paths. Right? And there's one thing slightly weird about this, which is that in the in-key condition, we don't actually get an effect, but let's ignore that. And let's just point to the sort of important thing here is that, these effects look pretty similar. So this is your sort of semantic garden path, your syntactic garden path. These are semantic violations. These are all done in French, by the way. But it's sort of comforting that at least these look almost exactly the same. So where does that leave us? I mean, so the shared syntactic integration resource hypothesis, I mean, in the name, it says syntactic integration resource hypothesis. So it doesn't seem like it's syntactic necessarily, right? If you can also get into these sort of semantic garden paths. And so you sort of are left with this question of like, well, it seems like something's shared, but I wonder what? And so the question ends up being, well, what is it that characterizes things like garden path sentences, these sort of semantic garden path sentences, but is different from a semantic anomaly like watching for angry pigs? And I think at least one potential way to characterize this distinction is that the garden path and semantic garden path sentences might require this sort of resolution of conflict between this information that you have that's just arrived, and this sort of built-up representation that you've constructed so far. Right? In the semantic case, that's not true, or at least much less true, because you didn't expect pigs, but you didn't have anything else built up that conflicts with pigs in that case. And this sort of conflict detection and resolution processes in the cognitive psychological literature is generally termed cognitive control, part of executive function. And here's a figure from a paper that is talking about the role of cognitive control in syntactic parsing of language. You might notice it looks not too dissimilar from Lonnie's figure in some ways. You've got your linguistic representations, and then you've got a couple of these sort of cognitive control-based processes. And the idea, the one that I'm particularly interested in here, is the left inferior frontal regions here, which supposedly are detecting and resolving conflict between internal representations. Right? So the idea is you have to sort of notice that there's some kind of conflict, and you have to somehow mitigate that and deal with it, however it is that you do that. And so you might wonder, might this same kind of cognitive control mechanism be involved in musical structure as well? Maybe that's part of what this shared resource might be. Now, the prototypical cognitive control task is the Stroop task. You've probably seen this before. It's a pretty straightforward task, been around for a number of years. And your job is to name ink color, or I guess the font color, lamp color, whatever it is that causes the color up here, of these words. So here you have to say red, here you have to say green, here you have to say something that's a little bit ambiguous based on this projector. But anyway, you get the idea, right? So the basic finding of the Stroop task is that people are relatively slow in these incongruent conditions because you have a conflict, both representational and responsiveness, between what the word says and what you've sort of read and what your response needs to be. In the domain of language, people have, there's been a couple of relatively recent findings that you can sort of see here, suggesting that the Stroop effect and resolution of syntactic and semantic ambiguity in language recruit overlapping brain mechanisms. Right? So these are both overlap maps between this January all paper is a syntactic manipulation, this is a semantic manipulation, but in both cases ones where you have this sort of conflict between a couple of different interpretations. And you might notice that these areas again look not dissimilar from the ones that we mentioned earlier that are involved in musical structure. Now notice that this is not a co-localization analysis. The language ones are. So one thing you might ask is, well, is the Stroop effect co-localized with musical structure? I'm not going to answer that question, because I have no idea. But another thing you might ask, maybe a first step, is to say, well, look, maybe is musical structure co-localized even with language structure? Maybe that's like a first question. And there's been a little bit of work on this recently. So most of the old work, what I mentioned before, are people who do musical structural tasks and language structural tasks, but not in the same people. And you say, oh, look, this looks like a language region, oh, this looks like a music region, everybody's happy. But what you really want to do is do it in the same people, right? So you can say, for a given person, do you get the same kind of neural activity for both language and music? The results that are out there so far are not super encouraging, but let me tell you about why I think they are not so discouraging. So here's one way of doing this, is you do a language localizer task. This comes from a Fedorenko crew up at MIT. And you do their language task looks something like this. You read sentences word by word, like a rusty lock was found in the drawer. You get some kind of simple question about did this string occur in what you just said, and you compare that to a non-words condition. Because neuroimaging stuff is always about subtractions. It's always about a comparison between two things. So the claim here is that reading this is going to activate whatever part of the brain is involved in language. Reading this is going to activate all the other crap you don't care about that is involved in looking at things on screens. And so if you subtract this, you're going to get language cortex. And in fact, you get, as you might predict, it appears that language is in the brain. In most of it, I would say. But what you can do then is you can say, okay, let's find some particular ROI, some particular regions that seem to be particularly robust for this difference. And let's say these are the important regions that we care about. And then what we'll do is we'll do this music task, and we'll see if the music task also shows a differential effect in those regions. So their music localizer that they use in this study is listening to either pop or rock music from the 50s and 60s, or pitch and rhythm scrambled pop and rock music from the 50s and 60s. The logic's the same, right? The idea is this tells you all about musical processing, musical syntax, whatever. This tells you about not that. Although, I don't know what the brain does when you listen to pitch and rhythm scrambled pop music, but I find it sort of implausible that it is nothing musical. Right? I suspect you might even imagine it's working harder, but let's assume for the moment that that it is nothing musical. And you get also a large chunk of the brain seems to be involved. And so then the question is, if we take the ROIs that are particularly relevant for language, based on this contrast, and we look at the musical contrast, what do we find? And they looked at a bunch of stuff, not just music, but we're just going to care about music. And so the claim here is none of them are. Here are all the reasons that are really important for language, which you can tell because the language is in the black bar, the non-words are in the gray bar. Nice big differences here, no differences here. Well, kind of. Nice big differences here, no differences here. Well, maybe. I don't know. I mean, my take is these don't look like no differences. And there's no particular attempt to equate the difficulty of these tasks or anything like that. So I'm not really sure how you say this is nothing. So I think this is entirely, these data can mean whatever you want. And what I want them to mean is that, hey, I got that one. What I want them to mean is, hey, it looks like an effect. Maybe it's just not as strong. Maybe the manipulation's not that great. So I think the answer to that is maybe. And notice that where you do, to the extent that you see this, it seems to be one of the places it's showing up is in these frontal regions, right, LaMERG, which is what I was just talking about as being involved in cognitive control. Some other reasons too. So how might we test whether cognitive control is involved in musical structure, as it seems to be in linguistic structure, at least to some extent? Well, I mentioned the Stroop task, so that's what we're going to use. This is work, by the way, from grad student Brooke Okada and Jason Reitman, who's a really quite impressively clever freshman undergrad who showed up in my lab last summer and taught himself the program. So it's a simple Stroop task. This is one that we use button press responses. So you basically push a button corresponding to the color that you see. We're going to look at neutral, because we don't care about Stroop facilitation here. We're looking at conflict. So really we want to know about interference. And incongruent, where you have to say green to blue. And we're going to do the same paradigm I showed you before, which is do it in where you have these sort of melodic context. So it's just going to appear at the end of a short phrase. And that phrase is going to end on the tonic, or it's going to end on some chord from a different key. Something kind of like this, maybe. Right, so you have to push the blue button in that case. Right, no problem. So what I'm going to show you here is also a different score. So here's your Stroop effect. So this is how much slower you are to push the button blue when blue is the word green versus when blue is a bunch of blue X's. And so positive numbers are a Stroop effect, and you can see that you have a nice Stroop effect. You can't really see this, but the dots represent individual participants. Box plot, represents some box plot stuff. So this is what accompanied by the tonic. So that's good. The music wasn't so distracting that it just washed everything out. But what about with the outer key chord? Well, you get a significantly greater Stroop effect. So that's kind of interesting, right? So it suggests that maybe there is something about this like harmonic manipulation that's interacting with cognitive control. Now remember, we didn't get interactions of timbre with these things, so you would probably want to know the same thing. Does timbral manipulation interact here? So same story, something like this. By the way, that is called a sitar according to MuseScore, which seems unlikely to me. But in this case, you don't get any such interaction. Okay? So now we find a Stroop effect that's not different as a function of the timbre of the chord that it's accompanying. So where does this leave us? So far we have the harmonic unexpectancy. Manipulations of harmonic unexpectancy interact with syntactic garden patterns, but also these semantic garden patterns, and also Stroop effects. So I think that these things together suggest that maybe cognitive control really is a shared mechanism here. And you can make another prediction if you want, which is that if it's the case that doing a lot of musical processing a lot of musical harmonically unexpected things, and resolving those is something that engages cognitive control, then you might think that people who do that a lot, by virtue of intensive musical training, like listening to complex, interesting music, might actually do better at cognitive control kinds of tasks. Now this has been looked at a little bit. There's some work that's inspired by work on bilingualism, where there's some evidence that bilinguals show some cognitive control advantages that presumably is related to their having to manage multiple languages. So might that be true of music? Ellen Bialystok has some data that says maybe. So what she finds is that musicians outperform musicians at kind of an auditory street task. And the way the auditory street task works is that you have to push a button, one button if the word is high and one button if the word is low, but what you hear is either high or high. Right? So you have an incongruent case where you have to respond to the word high at a low pitch or the word low at a high pitch, and she finds that musicians do better at this task than non-musicians. So that's interesting. On the other hand, musicians do a lot of stuff with pitch, so maybe that's not like hugely surprising. So you might want to know if musicians show an advantage even on cognitive control tests that are not pitch-based in some way. These are new data with Nick Davies, another student at Maryland, and Suzanne Yagi. And what we are relying on is the NBAC task, which is another classic cognitive control task. We've got some other tests too, but I'll tell you about if you are interested. The way the NBAC test works, though, is that you have the N is just a number, and I said, okay, we're going to do a 3-back. You're going to hear a bunch of things, and you have to tell me if the thing you heard is the same as what you heard 3 things ago. Right? So this is a cognitive control test because you have to maintain a certain number of things, but you also have to keep updating. So you have to remember what you heard 3 times ago, but then you have to forget what you heard 4 times ago, and remember what you heard 3 times ago when you hear a new thing. So it's kind of a hard task. Here, if you're listening to this, you say no, 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 yes, right? Because that note is the same as the note you heard 3 ago. So we do 2, 3, 4 backs. And then we do a more standard version that's not pitch-based. These are just random pitches, by the way. These aren't melodies or anything. The standard version uses letters, but it's exactly the same kind of task. And the question is, are musicians going to do better at the pitch one, at the standard one, or both, or neither, I guess? I guess by throwing neither in at the end, I sort of tipped it on the end. So on the pitch version, the musicians definitely do better. Although to be fair, what really seems to be going on is that the non-musicians are doing terribly, so they're hovering around 20% accuracy, so it's not an easy task. But you might imagine that part of what's going on here is that if you're a musician, you can label these pitches, right? So now you have a separate way of coding this, and that's pretty great. If you were not, maybe you can't, and it's pretty hard. So the real question ends up being the non-pitch comparison, and here we also find a significant difference. So this is about 40 people in each group. This is still ongoing, but these effects are pretty strong. So now we have all of this stuff. You have harmonic unexpectancy interacting with syntactic artifacts, semantic artifacts, group effects, and musicians seem to be doing better at standard cognitive control tasks, which I think suggests that cognitive control really is playing an important role in musical structural processing and might be part of what this shared resource actually is. Now, I don't want to say it's all cognitive control, right? I mean, I'm a reductionist, but not that much. So really, probably there's a whole bunch of kinds of cognitive processes that are involved. But I'm hoping that this kind of program is a way of starting to say, let's try to step away from just shared resources and say, well, what might those shared resources be? And I think that cognitive control might be one of them. So thanks to the people who did all the work, and to you guys. Make this lighter so that so I can see if it wants to. Yeah.
I was thinking of the experiments that they've done with working memory and chess masters, where they set up a board either as a plausible game or randomly, and so chess masters can much better remember the positions of the board when it was something that was a plausible game, but they do know better than anyone else when they do it as randomly. So I was wondering if you did something like the NBAC task with some domain-specific things, like let's say chess pieces. You compare regular people with musicians with chess masters. Like, would the musicians be better at remembering perhaps like the chess pieces than someone who doesn't play chess or play music, but presumably a chess master would still be able to do better in that test with chess pieces as images compared to even musicians? Is because same thing with the pitch thing where they have a language to describe it, so they're more familiar with it.
Yeah, no, I think that's very plausible that the chess masters would do better. My prediction based on this would be that musicians would also do better than non-musician,
Right.
but non-musician, non-chess players, right? That you might get some boost. But I mean, you got to take those data with a certain grain of salt, right? Because there are a lot of differences between musicians and non-musicians, and some of them are probably cognitive, that come as a function of musical training. Some of them are probably cognitive that come as a predisposition that makes you like to pursue musical training. Some of them are like socioeconomic that mean that you can afford to take music lessons, right? Like, there's a lot to, those data are preliminary, and there's a lot of things you need to try to control for in that kind of comparison. So I don't want to make too much of it, but I think that it's at least intriguing. And, you know, to the extent that you can find evidence for this, it's got some nice pedagogical implications too, where you can, you know, hopefully try to say, look, maybe music education has some value. Maybe chess education too. Get the chess lobby on my side.
I actually wanted to ask you what a musician is.
Oh yeah, that's a good question.
I mean, is it reading music? Is it having perfect pitch?
Yeah.
How do you define it as?
Yeah, for this study, we, the answer is, I think I have no idea. But for this study, what we did is we sort of said, well, let's stack the deck in our favor, but in such a way that we can get participants. So we required people who had at least 6 years of musical training and compared them to people who had less than 2. I actually do have some data on them, but I don't have it here. I can tell you that they do better at some of these tests of musical ability, which I think are largely tests of musical memory, but yeah, I think that's a really good question and a hard one to answer. Yeah, I mean, you might imagine, right, that the kind of musical experience you have would place different kinds of demands on cognitive control, right? So like theory might involve some, because you might be, you know, dealing with like pivot chords and interesting sort of transitions between keys and stuff, and maybe if you're a drummer, you have less of that, although you might argue that rhythmic syntax is, you know, equally complex. So yeah, I think it's a good question.
Or maybe a concert musician versus a jazz musician, where
Sure.
one is more geared towards the structure, perhaps, than memorization per se.
Sure. Or like people who do improvisation, right, where you have to like really deal with sort of accommodating to things in a very quick online kind of way.
Whether you can read music or, I mean, there are many musicians who can't read music.
Yeah, right. Sure.
Would they count as musicians? They wouldn't count as musicians.
In this case, I think they probably mostly would not. They're not selected besides having self-reported having over 6 or under 2. But we have a bunch of information. We collected a bunch of information on musical training stuff. There's data almost from last week, so I have no idea.
Sorry. I'm reminded of Nina Krause's work that shows musical training and facilitates hearing speech and noise, and even seeing the brainstem response is less affected by. Do you think it's the same kind of attention control?
Yeah, that's a really interesting question. So like, there is all this interesting work, a lot of it from Nina's lab and some others, suggesting that musical training is associated with these kind of perceptual advantages, right? That, as you say, show up as early as brainstem responses to, say, linguistic pitch and also musical pitch. I don't know, right? But I suspect that that's something slightly different, right? You could imagine musical training. I mean, the cool thing about musical training, right, is that this is a really intense training program that people do, like, under their own accord. You compare this to other kind of cognitive training studies that are out there where people do, like NBAC. There's a bunch of people who do NBAC training. Like NBAC training, you can train your brain, you can get an app for your phone that'll do it. But that's like mind-numbingly boring. So in musical training, you get people who do this thing, but it's a complex thing, and you might imagine that it'll have perceptual effects and that it'll also have cognitive effects. So I would argue this is more of a cognitive effect, and this might be more related to some of the other kinds of cognitive differences that you find as a function of musical training. But all that, again, with the caveat that, you know, these could be pre-existing differences as well. And with these data, at least I can't rule that out.
Just following up on Carl's question, I agree with your take on it. It seems to me that what you've discussed is something that's quite consistent with the SIR theory in terms of just being a friendly amendment that says essentially in the original theory, frontal regions were shared and posterior regions were specialized for things. And the executive control things are frontal. So it seems to me you're doing a very nice job of sort of specifying what types of things are going on frontally. The kind of perceptual effects that you're talking about seem to me not to be executive control. They're more, you know, it seems almost like these taxi drivers who you know, after cruising the city for years have expanded their perceptual representations. So, you know, you can imagine A1 or something in these musicians has also grown, and that's what's helping you on speech and noise, is that the primary auditory regions are better developed, more practiced, bigger, right, as opposed to these frontal regions.
Right, and there's even evidence that's consistent with that, right? Like if you look at gray matter density, musicians versus non-musicians, you find these sort of temporal regions that are more dense, presumably as a function of training, and that, right, that's quite different in the sense, I mean, yes, exactly right. This is not a challenge to the SSI range, it's, I mean, I hope that it's making it a little more specific. Okay, oh yeah.
So, yeah, I was just going to say. So, in the data set we talked about in the before the break, there's something else there. I'm not totally sure about yet, right? But whereas we see the additive pattern for the double violation for the more posterior P600 type effects, both in we also get frontal negativities both for the language and for the music. And those look super additive.
They look super additive?
Yeah. Yeah. And Daniel Casasanto tells me they have the super additive effects in fMRI in roughly BA44-ish, Broca's area, Broca's neighborhood. For the this is the same kind of stimuli they did with in Ted Gibson's lab, where they have like object subject relative clauses and sung sentences, right? Where they do things that.
Some of my favorite stimuli.
Aren't they? Yeah. Daniel sung those. Right?
Yeah, I know.
Yeah. He was a previous opera singer.
These ridiculous relative clause sense. They kiss the spy or look at that.
Yeah. Beautifully sung. Right?
It's like the worst opera ever. Sorry.
But I think there's these things are, I think, those kinds of patterns would be, I think, consistent with what you're saying, right?
Yeah, they are.
It wouldn't have to be an interference effect. I don't know if I understand exactly why we should ever get this kind of. I don't understand what underlies super additive effects. Period. But
yeah, well, I mean, that's actually a good and a really big question, I think. Right. I don't. Yeah, it's not necessarily the best way to get at these things, right? Like, in some sense, you could say, well, you could have things that are super additive for a number of reasons, right? And it could be the reason that you care about, but it could be a collection of other reasons as well. I mean, for example, there's no particular reason to think that the kinds of effects we're looking at are like linear in any meaningful way. Maybe they're like logarithmic or something, in which case you're going to get additive effects are going to look super additive, right? So part of it's, what about your scale? I mean, I think it's an issue. In some sense, I think your data are almost kind of comforting, even though I don't really understand them. Like, I don't know what they know, but like, I'm glad to see that one does not always get interactive effects no matter what one does, right? Because you could imagine that could be true, and then you sort of be like, well, I don't know if these mean anything. So we can just figure out what the difference is, and I think we'll be in good shape. So I think you're on the right track.
well, no, I think it's super cool, this idea of looking at the cognitive control stuff. I wasn't aware of the street thing. That's really cool.
Oh, thanks. Yeah, it's also data from like a couple months ago.
Yeah.
Hot off the not press, hot off the projector.
Yeah, so I'm not quite sure how to formulate this, but the cognitive control issues, it seems persistence in musical training could be something that happens for people who have cognitive control, right? So the causality in all of this is complicated.
Yeah, right. I actually think that in some sense those are the weakest data, right? Like yes. Let's just not waste time. I think that's a real issue. Yeah. It might be, but you also might imagine that that's something that develops over the course of training, right? You do learn to practice, and you sort of have to force yourself to do it, and presumably it gets easier. I mean, you probably need a certain amount to get started, but that doesn't necessarily mean you might not improve over training.
Is there evidence in other domains about executive functional cognitive control, how it develops with practice?
Yes. Well, so in fact, that work is in collaboration with Susan Yegi, in the middle there, who her bread and butter is doing cognitive control training. So she's really interested in sort of the malleability of cognitive functioning more generally. So she does these things where you have undergrads come in for, 4 hours a week for like the entire semester and do an hour of in-back training. And they get to the point where they can do 13, 14 back. I mean, it's amazing, right? And then the question is, does it transfer to anything else? And the answer is unclear. She's got some really nice evidence that it might. Other people have some evidence that it might not. So it seems like it can be trained at least within a domain. Whether it transfers out is, I think, less clear. But that's where I think maybe musical training is better in some ways than like NBAC training, because it's kind of broad spectrum, right? From a cognitive standpoint, you're doing a lot of different things. It's bad from an experimental standpoint because you have no idea what you just trained.
But it's more fun.
But yeah, right, and like, well, if nothing else, right, you come out of there instead of being like, hey, I can do a 13 back task. Like, that was a great music. At least you didn't, get Laura has your keyboard. Okay. All right, thanks very much.
Thank you.